Hello, my name is Gustavo Saez Cruz, and this is my project with Professor Banerjee on simulating classical spin waves. So what are the motivations? Um, well, when neutrons scatter off of a antiferromagnetic material that is in the ground state in terms of spins, it creates what is known as a spin waves. So essentially the spins of the two-dimensional lattice um, are in the ground state, and then a neutron comes in and scatters and creates a disturbance that essentially sends a wave in the spins. And I'm interested in simulating, or my project is about simulating these waves with creating a classical simulation of these waves. Um, then we can add quantum corrections to these, to what the simulation predicts. In the future project, we can add quantum corrections to what these simulations predict, and therefore we can see what happens when neutrons scatter off of the surfaces of materials that are made in the lab, in Banerjee's lab. So I will be using the Heisenberg model to essentially model the spins in the two-dimensional lattice. So our spins will be three-dimensional unit vectors, essentially, as you can see here, three-dimensional unit vectors uh, at each point in the lattice. The energy is given by the Heisenberg Hamiltonian, where J is the adjacency matrix, essentially, because so J can take on values, any value you want to model, but for our purposes, J is always going to be either zero if they are not connected or unity if they are connected. So it is essentially the adjacency matrix of whatever lattice we're working with. S is going to be the unit vector that represents a spin at the ith location. So as I mentioned earlier, the material is going to be at the ground state, and we want to learn how to find the ground state of if we start with an array or a network, a lattice, or we're given a lattice, we want to be able to find the ground state. And the way we do that is by the Metropolis algorithm. Essentially, the Metropolis algorithm works in three main steps. You pick a spin at random and change its angles, its polar or azimuthal angles at random, and then you calculate the delta H, which is the change in energy. If that change in energy is less than zero, then that means you decrease the energy, you keep that. So you keep that change, you don't throw it away. If the change is greater than zero, however, you keep the change, but with a probability given on the slide that is due to thermal, basically energy from the surrounding spins. There could be heat in the system that gives the spin enough energy to maintain that change. Again, the probability is given here, where KB is the Boltzmann constant and T is the temperature of the lattice. That we can assign a temperature to the lattice, and therefore we can calculate this probability. However, if it does not meet this probability, then you throw away the spin, you basically don't do anything, and you move on to another random site. And you want to do this as many times as you can, as many times as you can, because essentially the more you do it, the more accurate the more hypothetically, the more accurate your ground state is. The Metropolis algorithm is heuristic. That means that you're only approximating the ground state, and there's a chance that you can get stuck in a local minima. However, I'm working with sort of like low number of spins initially, so this is less. There is a less of a chance of this happening, so this will be satisfactory for the moment. Here are some examples of some ground states that I found using the Metropolis algorithm. So on A, we can see a simple hexagonal lattice, and we can see a ground state. On B, we can see a simple triangle lattice. And what's interesting here is that it seems that all triangle lattices share the sort of like 120-degree symmetry. So if you like rotate it, if you take the spins, there's like this 120-degree symmetry. I'm almost certain that's not by coincidence. Um, I can see one of these papers mention that. But anyways, that's just something I noticed. On C, we can see the sort of similar symmetry there. The angle between each of them seems to be 120. And then D, we can see just a larger hexagonal lattice. And we can see that it's still, the Metropolis algorithm still works for bigger lattices. So it sort of takes, the Metropolis algorithm also takes a lot of it's harder to compute for the larger the lattice you have. So one of the things I'll discuss later is the possibility of using other methods for finding the ground state. But anyways, moving on to the LLG equation. So once you have found the ground state, a neutron will will hit the ground state and will randomly pick a spin to switch. It's just gonna create a random. It's gonna take that spin and it's gonna basically give it a new angles essentially at random. And we want to model the dynamics of the waves that occur after that happens. So what I used is the LLG equation, which stands for the Landau-Lifshitz-Gilbert equation, which is used to sort of model classical spins like the system that I'm working with here. So originally, it only really had the LLG equation, which modeled the sort of, if you have an auxiliary field such as this, if you have an auxiliary field that you apply to a spin, it causes your spin to precess around the auxiliary field. However, you can this is not the whole story. So spins, when you apply it to when you apply an auxiliary field to spins, they relax onto the auxiliary field, and so they don't just precess around, but they actually relax onto the auxiliary field. And so the LLG equation describes this. Now here's the undamped LLG equation. Right here we can see it, and it basically just describes how each spin oscillates because of each other's spin. So one key difference between this application of the LLG equation and my application of the LLG equation is that here we have an external field. However, in here, it's actually each other spin that you're connected to that is creating a field, an effective field for you. So essentially, and we can see that here, your field that is that you experience is because of the other spins that you're connected to. So I haven't applied an external field yet, but still the LLG equation is useful here. So this one right here, this first one that we see is for just the oscillatory behavior. We can add the relaxation term by essentially adding this dampening term with the lambda. We're assuming that lambda is a very small number here, and this creates the relaxation. But enough talking about the sort of methods here. Let's see what actually happens. So here I have graphed a animation of what my results basically simulate. So this is the simulation right here. Essentially, I have worked on Python and I have downloaded the sort of the data and imported to MATLAB, which animates what happens. So one spin will be picked at random. It will be sort of just thrown off the ground state, that one spin, and this will create a wave, as we shall see. So here we can kind of see that it was initially in that sort of, each spin had that sort of angle between them. It had that 120 degrees angle between them. But then after we threw in that random neutron that scattered that random spin, we saw that like that a wave was essentially a wave oscillated through the entire system. And this is three-dimensional, so we can see how it started two-dimensional because it's just how I decided to initialize the ground state, but the random change of the spin was three-dimensional, so it pops out into 3D here, and we creates a three-dimensional spin wave. We can see additional. So that was for a fairly large triangular lattice. We can also see what happens for a very small triangular lattice. So just running this real quick. Here we can see the ground state from the Metropolis algorithm. And here it's simulated. So these are the XY components. And importing that data right here. So this is for a small triangular lattice. We can still see that, it creates a sort of wave. So whereas it started in the ground state, you take it out of the ground state, and it creates a wave that oscillates in your system. So yes, so that is the result. So I was able to create a simulation for any arbitrary lattice that I'm given. But for right now, I am assuming that J is unity when they are connected. Some interesting things that could be done in the future is see what happens when, oh, apologies. Let's see. Yes, some interesting things that could be done in the future is to see what happens when J is not just unity. You know, what if there is some asyntropy or eccentricity, where the direction does matter? You know, there is a stronger coupling in the X direction than in the Y and the Z. That could be some interesting things to add to this. And yes, so another thing would be that using a more accurate method to find the ground state. Not only more accurate, but faster and more efficient. Again, the Metropolis algorithm takes long. It takes a lot of time for larger systems. However, there are methods out there like the Loninger-Titze method that could be faster and more accurate for larger systems if we make certain assumptions. And yes, that is the conclusion to my talk.